Today we're going to talk about hydroelectric energy. And so we'll start out with looking at gravitational potential energy, a reminder. We'll talk about how hydroelectric energy works, look a little bit about its footprint in the U.S. and globally, and then look at some of the pros and cons. So hydropower is one of the oldest methods of obtaining energy. And what it does is it taps into the solar-driven evaporation cycle, which we'll talk about, where solar energy lifts water, giving it gravitational potential energy. And in the U.S., we get about 2.8% of our energy from this and 7% of electricity. And globally, hydropower accounts for about 9% of energy and 16% of electrical production. So just first, a quick note on gravity. The gravitational force is actually really weak. It doesn't really seem so in our daily experience, but as the author suggests, just think about the fact that a little handheld magnet can lift a paperclip, overwhelming the gravitational pull of the entire Earth. And so in reality, electromagnetic forces are about 40 orders of magnitude stronger than the gravitational force. But we don't notice that because those forces tend to balance out, where gravity doesn't have a positive and a negative, at least not that anyone knows about. And so it has a much larger impact on us from day to day. Then again, a quick reminder, gravitational potential energy. So again, when we lift something up, we give it potential energy. Again, this comes from the electrical attraction between whatever object we're talking about and the Earth. And we can represent this with our formula, gravitational potential energy equals mgh, where again, for us, we're going to approximate the gravitational constant as 10 meters per second squared. So just a quick review, how much gravitational potential energy is stored when we lift a 20 kilogram box of books to a shelf that is 2 meters high. And so we take that formula, and I'm going to put the approximately because we're using a little bit of a different number for G. So 20 kilograms, 10 meters per second squared, and then a height of 2 meters. And when I multiply that out, I get 400 joules of energy, again, when we lift that box of books up on top of the shelf. And let's do another example, just to kind of look at comparing gravitational potential energy to other forms of energy. So a typical AA battery has a charge rating of 2.5 amp hours and operates at 1.5 volts. And so we're going to look at, first of all, how much energy does this battery contain, and then what mass would have to be lifted to a height of, say, 4 meters to gain an equivalent amount of gravitational potential energy. Okay, so we'll start out by looking at these two numbers. So if I take 2.5 amp hours and multiply it times 1.5 volts, the result I get is going to be 3.75, and then the volts times the amps gives us units of watts. We know that current times voltage gives us units of watts, and then watts hours. So again, 3.75 watts hours, this is a unit of energy. Now to convert this over, what we're going to do is take this and just convert it into kilowatt hours. So we know that 1 kilowatt hour is going to equal 1,000 watt hours. And when I did this myself, I got 3.75 times 10 to the negative 3 kilowatt hours. And so this would be the answer to the first one. How much energy does this battery contain? And so now we want to do, though, is compare this to this gravitational energy that we're talking about. So the first thing we'll do is convert this into joules. And so I'll take that 3.75 times 10 to the negative 3 kilowatt hours. And then we know that 1 kilowatt hour is 3.6 times 10 to the 6 joules. And so when I ran through that calculation, I came out with 1.35 times 10 to the 4 joules. So quite a bit of joules. And then, again, what we're trying to do here is just sort of compare and contrast. And so let's take this number and look at how much mass, again, we'd have to lift up to a height of 4 meters to equal this same amount of energy. So I write that in there, and I'm just going to solve this for the H. And so it's 1.35 times 10 to the 4 joules. And again, so G, so this will be divided by the G and the H, which we're going to write here. So the G and the H, the G constant, of course, we use 10 meters per second squared, and we're talking about a height of 4 meters, just to kind of pick that out of a hat. And so when I did that, I got about 337 kilograms, which, roughly works out to be like, 4 or 5 people. So it's pretty incredible to think about, the actual energy content of a AA battery is the same as if you lifted 4 or 5 people up 4 meters. All right, let's move on. All right, so hydroelectric energy is the process of producing electricity from gravitational potential energy using a lake or some reservoir of water. The reservoir of water behind a dam, as in the picture here, creates pressure that forces water through the turbines. And that turbine drives a generator producing electricity. The amount of energy available works out to be the gravitational potential energy corresponding to the height of the reservoir compared to the water level on the other side. So here in this picture, it's roughly this height here, this height H. So again, it's from sort of the top of the reservoir down to where the water level is on the other side. And one nice thing is that this particular process approaches 90% efficiency, which is pretty high, right? And how does it do this? Well, basically, we just have really good electric motors. They don't have a lot of friction, low friction turbines and stuff like that. And so we actually are able to, get, again, 90% of the sort of potential energy that we possibly could. And here's a picture of the biggest right now hydroelectric dam. This is Three Gorges Dam in China, and you can just kind of see in the picture here, again, there's a difference in height. Sort of on this side is where the top of the reservoir, and down here this is the water coming out after spinning the turbines. Here's a little sort of mock-up sort of this situation. All right, so to compute the power available, we need to know the height of the reservoir and the flow rate of water. So let's do an example of a dam that's got a flow rate of 2,000 meters cubed per second and a height of 50 meters. And so we'll start with the flow rate. So 2,000 meters cubed per second. And so this guy down here just reminds us that 1 cubic meter of water has a mass of 1,000 kilograms. And so we can multiply this by one of our special number ones, 1,000 kilograms over meters cubed. Those meters cubed cancel, and we get 2 times 10 to the 6th kilograms per second. So in this particular dam, we have 2 times 10 to the 6 kilograms pouring out every second. So to look at the energy and the power, we're going to use our gravitational potential energy equation, which is mgh. And so remembering that we have 2 times 10 to the 6th kilograms pouring out every second. G we can approximate as 10 meters per second squared. And again, in this case, the dam has a height differential of 50 meters. And so when I went through and multiplied this, I get 1 times 10 to the 9 joules. So the water that's rushing through is the equivalent of gravitational potential energy of 1 times 10 to the 9 joules. And since that's every second, then I can say the power that we're supplying here is 1 times 10 to the 9 watts, because it's that much energy coming out every second. And then, of course, just the caveat that this is about 90% efficient, so we only get 90% of that. But that's the the potential that we could be getting. So one thing just to mention, you might hear people talk about the capacity factor, and that just goes along with, sometimes there's a certain capacity of power that we can get from hydroelectric, but only a certain amount that's actually being used. And so right now, the capacity factor in the U.S., we get using about 33 gigawatts of power, and there's the potential to use 80 gigawatts. And so to figure out the capacity factor in this case, you get something there of 41.25%. So that's how much of the actual performance that we're using versus what we could be using. The textbook goes through a discussion of the evaporation cycle. I just wanted to kind of talk about that briefly just to make sure we're all on the same page. So the first thing that the book looks at is this idea of heat of vaporization. So the sun needs to produce about 2250 joules per gram to evaporate water. Now, when the water turns into a cloud, this energy gets released, and so it's just sort of there for a little bit. But during this process, the sun is essentially bringing this water up to a height. And so just for examples, we're going to say that height is 5 kilometers. And so we're going to try to just sort of calculate briefly what the gravitational potential energy would be for that 1 gram of water. And so if it's 1 gram, then we can write that as 0.001 kilograms, right, for our formula, mgh. Our gravitational constant is 10 meters per second squared, and then, of course, the 5 kilometers, which would be 5 times 10 to the 3 meters. When I went through this, I got about 50 joules. So the sun evaporates the water and then basically gives it this extra 50 joules, again, for every gram. And then what happens is the water rains down. And so some of that water goes into the ocean, and then basically that energy is gone. But some of it, if it lands on land that's high enough in order for, again, in theory, to use this energy for, it's like a hydroelectric plant, then it can actually be used. And what works out is a couple things. So from this 50 joules, basically the average height of land on Earth is about 800 meters. So then when the water lands, it's going to basically have 8 joules left of that energy. Now that's the land part, and if you remember, roughly we have about 1/4 of Earth is land. And so roughly out of this 50 joules that the sun gives each gram of water, we're going to have 2 joules left over. Just a kind of quick sort of discussion of how that works. So it's estimated that overall through hydroelectric, the Earth has the potential capacity of about 2 terawatts of power, which we're using, I think, roughly about half of that. And again, remember that our current energetic output is 18 terawatts. So sort of the take-home message is hydroelectric power, while having a lot of positives, can't possibly come close to satisfying the present power, global power demand. And then finally, like we will do for all of our different sources of power, we're going to go through some of the pros and cons. So for hydroelectric energy, pros, it's natural. There's no pollution in the process. Technologically, it's pretty simple. Again, this has been used by people for a long time. Very highly efficient. Now, when we talk about the life cycle CO2 emission, and when we talk about this, we're talking about how much CO2 is emitted in the whole process. And so this is where one place where, again, hydroelectric energy comes out really well. It's about 4% that of using fossil fuels. And these facilities, again, being pretty simple, can last a long time. Now, there are some negatives, and so it's the cons. So most of them are sort of just about the actual location. So silt can build up behind the dam, which can render the dam useless or even dangerous. It does require semi-permanent flooding of a certain habitat, which you need to keep that in mind. Seasonal, there is some seasonal variability in the power. Basically, the amount of water can kind of ebb and flow. And so this obviously can also present a flood danger, and finally, just not a viable option everywhere. And so here's a map of just looking at how much, where the actual generation is happening in the United States. And again, there's only certain places where this is a really nice way to make energy.